Hi, I am Fariha from University of Massachusetts Amherst. Today I am going to demonstrate our work ExTuNe that explains tuple non-conformance. This work was done while I was interning at Microsoft with Ashish Tiwari, Arjun Radhakrishna and Sumit Gulwani. First, let's talk about the problem. Suppose that you have trained your favorite machine learning model with these colorful apples to predict their color. Now you deploy your model and your model seems to work pretty well for these new apples. So far, so good. But now you encountered this new thing, a strange watermelon wedge. Now the question is, would you trust your model's prediction on this? In data-driven machine learning, we sometimes encounter tuples for which the learned model is very much likely to make an incorrect prediction. This usually happens when the tuple is significantly different from what the model has seen so far. These are non-conforming tuples, that is, they don't conform to the training data. A key application of detecting non-conformance is to figure out when we should trust predictions made by machine learned model and when not. This becomes an extremely critical issue when high-stake decisions are taken based on these predictions. Wrong predictions made by machine learned models have caused serious issues in the past, such as unsafe medical treatment and unsafe self-driving, which even caused human death. Many of these failures are due to non-conformance of the new data tuple with respect to the training data, something the model has never seen before. So the first question is, how can we detect tuple non-conformance? And once we have detected that a tuple is non-conforming, the next question is why? What is causing the non-conformance? The focus of this demo is on the explanation, but before that, I am going to give a brief overview on the detection techniques on which ExTuNe is built. To detect non-conformance, we use our previous work on data invariants. Data invariants are a set of constraints that capture the common properties or invariants of the data. To detect non-conformance, we simply check whether a new tuple satisfies or violates the data invariants. When a tuple violates the data invariants, then it is non-conforming. As an example, consider this health dataset with three attributes: height, weight, and BMI. A simple data invariant on this dataset is that BMI should be between 10 and 40. A slightly more complex data invariant is that 28 times height minus weight should be within the range minus 40 and 30. I will skip the details of data invariants and the techniques we use to compute good data invariants in this talk, but at a high level, data invariants are constraints on linear combination of attributes. Now suppose that a new tuple arrives with BMI 231. This tuple is clearly non-conforming because it violates the data invariant that states the typical range of BMI. Now another tuple arrives with BMI 20,000. This tuple is way more non-conforming than the previous tuple. To capture the degree of non-conformance, we measure how much it violated the data invariants. More violations imply more non-conformance. So far, I have talked about how we detect and measure the degree of tuple non-conformance. The goal of this demo is to provide an explanation so that we can understand the causes of these non-conformances. Specifically, ExTuNe has three goals. First, to rank and visualize the non-conforming tuples based on their degree of non-conformance. Second, to provide tuple-level explanation for non-conformance. That is, given a non-conforming tuple, which of its attributes are responsible for its non-conformance. And third, to do the same for the entire dataset and not just one tuple. That is, showing the aggregated responsibility of each attribute across the whole dataset. I will now give a high-level overview of the inner working of ExTuNe and then proceed to the demonstration. Ranking non-conforming tuples is straightforward. We compute invariant violation scores for all tuples and then sort them by decreasing order of violation scores. For tuple-level explanation, we want to figure out which attribute or interaction of attributes of a tuple are responsible for the non-conformance. For example, is the abnormally high BMI causing these tuples non-conformance? Or is it an interaction between height and weight? The key idea behind ExTuNe is to perform an intervention, that is, to change a value in the non-conforming tuple and set it to the attribute mean over the dataset. And then we observe the causal effect, how it affects the tuple's non-conformance. If the intervention on an attribute makes the tuple no longer non-conforming, then we blame that attribute for causing its non-conformance. But in many cases, multiple attributes cause tuple non-conformance. If intervening on a single attribute doesn't work, then we try intervening on different subsets of attributes until we can make the tuple conforming. For example, in this case, both height and weight would get the blame and share equal responsibility for causing non-conformance, because this person is too tall and has a very low weight. ExTuNe's principle is based on actual causality and responsibility. I will skip the details in this talk, but please refer to our paper for more details on this. I will now proceed to demonstrate ExTuNe. So let's get started with the demo. ExTuNe's interface is built within a Jupyter notebook. At first, I am going to upload the dataset. I am selecting the cardio dataset, which contains information about people and whether they have cardiovascular disease or not. The dataset is now uploaded. Now I am going to split the dataset into two partitions. In one partition, I am going to keep only the healthy people with no cardiovascular disease, and I will use this as the reference data. Here, a 0 value for the attribute cardio means that the person is healthy. My goal here is to see if people with cardiovascular disease conforms to healthy people, and if not, why. Now I am going to give ExTuNe the healthy people's data and let it learn the data invariants from it. So the learning is done. I am now uploading the cardiac patient's data. So I want to see the top 10 most non-conforming people among these cardiac patients. And this is what we find. The tuples here are ranked from most non-conforming to least non-conforming, and the degree of non-conformance is shown in this violation column. Now let's take a closer look. As you can see, the color intensities of these cells are different. A darker color means more responsibility for non-conformance, and a lighter color means less responsibility for non-conformance. So let's focus on this row. The primary reason why this person is not conforming to healthy people is that she has abnormally high weight. Here weights are in kilograms, so 200 kilograms is about 440 pounds. So now let's take a look at this other row. This person is non-conforming because his systolic and diastolic blood pressure are abnormally high. A healthy person's systolic blood pressure should be about 120 and diastolic blood pressure should be about 80. For this person, it is 200 and 170, which is really high. So here, ExTuNe is explaining not only who are non-conforming, but also 1, how much they are non-conforming in this violation column, and 2, what is the relative responsibility of each attributes for causing the non-conformance. Now I also want to know what is each attribute's share of responsibility for causing the overall non-conformance in the entire set of cardiac patients. And here we go. As you can see, systolic blood pressure here is identified as the most responsible attribute for the overall non-conformance. This is followed by diastolic blood pressure. This is very meaningful since it is well known that abnormal blood pressure is the primary indicator for cardiovascular disease. So these two attributes are followed by weight, cholesterol level, and smoking habit. These 3 attributes are also well-known risk factors for cardiovascular disease. ExTuNe is generating these explanations entirely in a data-driven manner. There was no a priori knowledge about high blood pressure or high cholesterol being key cause of cardiovascular disease. It's all just based on data, and ExTuNe would work just as well for any other dataset. Lastly, I want to show you an interesting discovery we made using ExTuNe. We applied ExTuNe on the United States state-wise COVID patient statistics dataset. This was done during late March. We learned invariants on data over a week and tried to find anomalies in the next week's data. During training, a very simple invariant was learned. The total number of tests should be equal to the sum of positive and negative cases. When we took a closer look at the non-conforming tuples, we found a data entry error due to a typo. The total number of tests for New Jersey should have been 298, but instead it was mistyped as 218, and ExTuNe correctly explained the cause of the error. The final point I want to make is that identifying a tuple as non-conforming only means that we should be careful about predictions made on that tuple by any machine learned model, since the model never saw such patterns during training. It does not necessarily mean that the data is incorrect. But data error is one possible reason for tuple non-conformance, and ExTuNe can locate those errors. Thank you for listening. We'll be happy to answer any question over the communication channel.